Hi Math 3 students, Mrs. Robinson here to work Practice Benchmark Chapter 5 with you. We are working on rational expressions in this first problem. We're going to state any excluded values. Remember, when you're working with fractions, you can never divide by 0. Rational expressions are like our fractions with variables. Remember, a rational number is anything that can be written as a over b. So rational expression, we've got variables and we've got a fraction here. So we can't divide by 0, so we have to watch out when we have a variable in the denominator and make sure this denominator doesn't give us 0. Here I have a value x. What would make this denominator 0? I need to state that value. Let's start with that. Here, if x were equal to 1, 1 minus 1 is 0, and this would be 0, and I can't divide by 0. I don't know how to divide by 0. It's the weirdest thing in math. You can't take something and divide it up 0 ways. Doesn't exist. So I'm going to say x cannot equal 1. There's my excluded value. Now to simplify, I simplify just like I would if I was simplifying a fraction. Okay, I pull out their common term and go ahead and divide them out. So if I have 4x minus 4, let's see if I have a common term here that I can pull out. I can factor out a 4, and I'm left with x. And then if I divide a 4 out of 4, I'm left with minus 1. So this would be 4 times x minus 1. And on the denominator, I just have x minus 1. Now remember, I can't divide things out that are subtracted. You can only divide things out that are multiplied. The opposite of multiplication is division. 4 is now multiplied by the quantity x minus 1. And on the denominator, I also have the quantity x minus 1. So these divide out and leave me with 1. Anything divides into itself and makes 1. So now I have 4 times 1, which is just equal to 4. So 4 is my solution, and I need to exclude my excluded value. X cannot equal 1. All right, I want to simplify number 2. Now I can't go ahead and go dividing things out. I can't divide these. A lot of people, when they're not understanding what's going on here, they might think I can go x squared divided by x squared. I cannot do that. Do not do that. X squared is added to 2x, which is subtracted from 24. This is a whole quantity when I know what x is, okay? I can only divide things out when they're multiplied. These are added. I cannot divide things out like that. But I can try to factor this so that I have two quantities that are multiplied together on the top and the bottom. I have a trinomial, and if I have two quantities that are multiplied together, then I can go ahead and divide them out. Now I have a trinomial that I hope I can break into two binomials. So I'm going to go ahead and factor this into x and x. And I'm trying to figure out the factors of 42 that will add up to be, negative 42. That will add up to be negative 1. Well, I know 42 is 6 times 7. And I want one of them to be negative for this to be negative. I want this to be negative, so I'm going to make the 7 negative. 6 plus negative 7 is negative 1, and that will work. So I'm going to go plus 6 and minus 7. On the denominator, this factors into x and x. 24, so I want the factors of negative 24. That's a 4. That might add up to, let me try that again. Negative 24. That might add up to be 2. So let's see. 6 times 4 gives me 24. And if I could get one of those to be negative, they could add up to be 2. I do have a negative 24 here, so I'm going to go negative 4 because when I add these, I want positive 2. So 6 minus 4 does give me positive 2, and there's my terms. Plus 6 minus 4. All right, numerator is this and denominator is this. Now I have two things that are multiplied. I can go ahead and divide. So let's see, do I have any common terms I could divide into each other? Let's see. X plus 6 divides with x plus 6, and it leaves me with 1. And then nothing else, and 1 times anything is itself, so I'm left with x minus 7 on the numerator and x minus 4 on the denominator. Now I'm going to go ahead and state my excluded values. Now looking at the denominator, if I just have my simplified version, I'm going to say, all right, x better not be 4, because if it were 4, this would be 0. But go back to your original. X couldn't be 4, and x also. X cannot be negative 6, okay? So x cannot be 4, x cannot be negative 6, because here if it was negative 6, none of this would happen, because if it were negative 6, this times this would be 0, and this wouldn't work. There's my excluded values, and there's my solution. Okay, so looking at Here I have x minus 2, or excuse me, x squared minus 4 over 2 minus x. Now let's see if I can make factor out anything for my numerator. And I'm looking at this and thinking, I've got the difference of two perfect squares. So this can factor into x, and 4 is 2 squared. So it's going to be minus 2 plus 2. Okay, and then when you multiply it out, your middle terms fall out. That's the beauty of the difference of perfect squares. Now that x minus 2 looks almost like 2 minus x, except for even if I rewrote this, this would be negative x, and this would be a positive 2. So still, negative x and positive 2, nope. Negative x and positive 2, nope. But how about if I force this? What if I take this and I factor out a negative 1? So if I take this and factor out a negative 1, I'm going to pull out a negative 1. And by doing that, that becomes positive x, and that becomes negative 2. And if I multiply it back in, I get negative x plus 2. If I do that, then I've got terms that will cancel. So let's go ahead and force this denominator to be this. Now, I can go ahead and cancel x minus 2 divides into x minus 2 and leaves me with 1. The negative 1 is still there, so what I'm going to have is 1 times x plus 2, which is just x plus 2. And on the denominator, I have negative 1. Now I can go ahead and divide this by distributive property into the numerator. So negative 1 into x would be negative x, and negative 1 into 2 would be negative 2. And there is your solution. Now look at your excluded values. If x were 2, the original, here in the original, if x were 2, this would be 0. You don't want your denominator 0, so make sure you say x cannot be 2. And there you have it. Okay, 4, we're going to multiply. It's easiest to just multiply straight across and straight across, but if you can go ahead and simplify or divide out any common factors, I would do that. So here I've got y squared minus 25. I can see this is the difference of perfect squares. Let's write it out as the difference of perfect squares. This would be y minus 5 and times y plus 5. So that's what this is. And now I can go ahead and say this doesn't factor anymore. I can't pull anything out of this. Let's go ahead and cross cancel. On the bottom, I have y minus 5 times 3y. On the top, I have y minus 5 times y plus 5 times 4y. Everything is multiplied, so I can go ahead and cancel. Y minus 5 cancels with y minus 5 and leaves you with 1. And here, this y is multiplied by 4, but that y would cancel by this y is multiplied by 3. The y's would cancel and just leave me with 4 over 3. Y divides into y and leaves me with 1. So let's go ahead and multiply what I'm left with on the top. 1 times y plus 5 times 1 is just y plus 5. And then I do have a 4 here. Don't forget that 4 times 4. And on the denominator, I have 3 times this became a 1 and that became a 1. When I divided these out. So 3 times 1, which is just 3. So my final, I would have 4. If I wanted to distribute this, this would be 4y plus 4 times 5 is 20 over 3. Now go ahead and state your excluded values. Here, y, if I erase this, and you can see what was there originally, y cannot be 0, because if this were 0, I'd multiply by everything and everything would be 0. So make sure you state y cannot be 0. And in this scenario, y could not be 5, because if y were 5, 5 minus 5 would make 0. So y cannot be 5. And there's your solution. Just so you know, this solution is perfectly fine. This solution is perfectly fine. If you want to put the 4 in front, perfectly fine. Okay, so number 5. Let's look at number 5. S squared minus 2s over this trinomial divided. So we're dividing now. Now remember when you divide two fractions, this is just old school fraction dividing. Keep, flip, change. KFC. Keep the first fraction, flip the second fraction, change the divide to multiply. Remember chicken when you're dividing fractions. Okay, the same with polynomials. We keep this first one, s squared minus 2s over s squared minus 7s plus 10. We flip the second one, s minus 5. I hate 5s and s's. They look the same. over s minus 4, and we change divide to multiply. And there we have it. Now we've got a multiply problem, and we're going to go ahead and multiply across the top, across the bottom, but let's go ahead and factor out anything we can so that we can divide out common factors. S squared minus 2s. I wrote two binomials there. It's actually not the difference of perfect squares, but I can pull out an s. I can factor out an s, and I'm left with an s, and I pull an s out of here, I'm left with just minus 2. So if I factor out an s, I'm left with s times s minus 2. On top, I have s minus 5. That doesn't do anything. That's an s, and that's a 5. All right, on the bottom, let's see if this trinomial factors into a binomial. This would be s and s. We need the factors of 10. That will add up to negative 7. So 5 times 2 is 10. I could get a negative 7 if they were both negative. A negative and a negative does a positive, and I add those and I get negative 7. So negative 5, negative 2. And then here I just have s minus 4. I don't have anything I can do with that. And I go ahead and put the parentheses around it so you can see this is all multiplied together. This is all multiplied together, so I can go ahead and cross cancel and do some division here. Cross cancel any factors that are common. So s minus 2 and s minus 2 gives you 1. You can write a 1 down here if you'd like. Let's see. S minus 5 and s minus 5 give you a 1, and that's all you can do. That's it. So you have s times 1, which is just s. And on the bottom, I'm just left with s minus 4. And that's all I can do. I can't divide this into this because this is a whole quantity here. All right, and I need to go ahead and state my excluded values. So I'm going to come back to my original. This is my denominator. This is also my denominator. So here I'm going to look and say, all right, well, when I factored this, I got these two terms. So I'm going to say here, s cannot be 5 here, and s cannot be 2 here. S cannot be 2 here. And then my original denominator was 5, so s cannot be 5 here, and I've already said that. So s cannot be 2 and s cannot be 5. Okay, remember, keep flip change with these division problems. Keep flip change, KFC, finger licking chicken. So I've got a division problem, so I keep the first fraction. I flip the second one. This one doesn't have a denominator. Anytime that happens, you give it a denominator of 1, and you turn that to multiply. So I'm going to write this as x squared minus 4 over x minus 8. Keep the first, flip the second. 1 over x minus 2. Change that to a multiply. Now you can go ahead and work the problem. It's a multiply problem, across the top, across the bottom. This, let's break it into its perfect square. It's the difference of perfect squares. So x minus 2 times x plus 2 is how this would factor, and my pen is giving me problems. Let me try that again. X plus 2. All right. And then times 1, which is just 1. And then on the bottom, I'm just going to have x minus 8 times x minus 2. So I can go ahead and cancel anything that cancels. Let's go with x minus 2 cancels with x minus 2 and leaves me with 1. Nothing else cancels. There's no other common term. So multiply across the top. 1 times x plus 2 times 1 will be x plus 2. And across the bottom, x minus 8. And there's your solution. Okay, guys, I just realized this is my bad, but these two are the exactly same problems, but they're written a little differently. So let's just make sure that you can do it in either form. This is a fraction divided by another term. So this would be a complex fraction. So this would be this big fraction, x squared minus 4 over x minus 8, divided by this. Now there's no denominator here. Give it a denominator of 1. So I have a fraction, a big divide bar, and another fraction. So I'm going to keep the first, flip the second, 1 over x minus 2, and change the big divide to a multiply. And then once again, I'm left with that problem I just did. So x minus 2 times x plus 2, and times 1, and then here's your denominators. And then these cancel and you're left with x plus 2 over x minus 8. Okay, number 8, I get a sneeze. All right, adding and subtracting rationals is a bit tougher than multiplying and dividing. Adding and subtracting, just like when you add and subtract fractions, you have to get a common denominator. So let's start with this number 8. Look here, yay, we have a common denominator. So when you have a common denominator, you just add numerators. So I'm going to go x plus 5, and on the denominator, I keep my denominator of x squared minus 25. Now before you're finished, you need to see if you can reduce your fraction. Just like when you add fractions and you keep your common denominator, reduce it at the end. This x squared minus 25 does factor into x minus 5 times x plus 5. And if you look, x plus 5 and x plus 5 cancel into each other and leave you with 1. And you're left with 1 over x minus 5. So this is the most reduced solution when you add those together. All right, careful with this subtract sign here. I have to get common denominators. X plus 4 and x minus 4 are not common denominators. So just like you did before, you have to get a common denominator with a common, the least common denominator. These two don't have a factor in common. You literally, to get the common denominator, have to multiply the two together. So x plus 4 times x minus 4 will be my common denominator. So to get this fraction to have this denominator, I need to multiply the top and bottom by x minus 4 because it's missing. So I have to multiply top and bottom by x minus 4. And when I do that, I have this denominator, and on the top, I'm going to have 6 times x minus 4. Distribute that, that will be 6x, and then 6 times negative 4 will be negative 24. So that's this fraction. Now this fraction also has the denominator of x plus 4 times x minus 4. And you could have written it all as one fraction if you wanted. This is a minus. I want you to be aware of that minus. Now to get this to have this denominator, I need to multiply top and bottom by x plus 4. So multiply top and bottom by x plus 4. Sorry, the pen is not working again. Distribute the 5 here. This negative is going to distribute to everything, so be aware. First, I'm going to distribute the 5, and I'm going to get 5x and distribute the 5 to here plus 20. Now careful, this is actually minus this whole quantity. So I'm going to go ahead and rewrite this with one denominator. My denominator is x plus 4 times x minus 4, now that they're common. And I go ahead and subtract the numerators. Well, when I do that, I distribute this to both terms. So this is going to be minus 5x minus 20. Now, a lot of students don't distribute that negative to the second term. Please be aware when you're subtracting, you subtract everything on the numerator. All right, so when I do that, I go 6x's minus 5x's, and I get 1x. So I did those. And I go negative 24 minus 20, and I'm going to get negative 44. So I have x minus 44 over x plus 4 times x minus 4. And you're done. All right, number 10, you got to get common denominators. These two don't have anything in common. I have an x minus 2 and an x minus 5. So in order to get common denominators, I have to multiply them together. X minus 2 times x minus 5. Okay, so I have to get this fraction and then this fraction, x minus 2 times x minus 5. They both need this denominator. So to get this one to have this denominator, I multiply top and bottom by x minus 5. And to get this one to have this denominator, I multiply top and bottom by x minus 2. I don't know why that x does it like that. Okay, so let's go ahead. So the first fraction, if I multiply top and bottom by x minus 5, I get this denominator. And I'm going to distribute 7 times this. So this will be 7x minus 35. This is an add between the fractions, and multiply top and bottom by x minus 2 to get this denominator. So it's going to be 2 times x and then 2 times negative 2, which is negative 4. Now go ahead and add numerators, and your denominator is still x minus 2, it's your common denominator, times x minus 5. And the numerator, go ahead and add them. 7x's and 2x's make 9x's. So those terms are in common. I did that. And then negative 35 minus 4 will give you negative 39. Now see if any reducing can be done. Even if I pull out a 9, that's actually not going to work. 9 doesn't divide into 39. So I think you're done. So A piece of craft wood, length 5/3 or x minus 3 meters, was cut into 2 pieces. If one piece is 2/x plus 3, depending on what x is, express the length of the other board in meters as a rational expression. So basically it's saying you start out with this, 5/x minus 3, and this is one of the pieces. So this is the whole piece, the whole board, whatever it is. And this is one of the pieces, let's say right here. This is one of the pieces right here. This would be the 2/x plus 3. And the whole board would be 5/x minus 3, this amount, okay? Express the length of the board in meters as a rational expression. If one piece is this, we're expressing the length of the other board. So we want to express the length of this. So to express the length of this, we would just take the whole piece and subtract off this piece, and that would give us that piece. So I would just write 5/x minus 3 minus the piece we know, 2/x plus 3. And that would be the rational expression. Now I'm going to simplify this. I'm not just going to say, well, there it is. I need to simplify it. Unfortunately, I do not have a common denominator. They don't make it that easy. So I have to get the common denominator of x minus 3 times x plus 3. Okay. So I'm just going to write this once, so I'm going to put these all together anyways. So I'm going to go ahead and write, to get this to have that denominator, I need to multiply top and bottom by x plus 3. Top and bottom by x plus 3. If I multiply top and bottom by x plus 3, I get this denominator. So I'm going to go 5 times x, which is 5x, then 5 times 3, which will be 15. Now this, I have to multiply top and bottom by x minus 3. Now I can write another fraction here, but they're going to have the same denominator. I'm going to smush it together anyway, so I'm just going to write them all over one denominator. So when I multiply this, I get this denominator, and then I'm going to distribute this. Now careful, this is minus 2. So I could go ahead and distribute this and then subtract off the second fraction, or I can do it all at once and go, this is minus 2 times x, which would be negative 2x, and then minus 2 times negative 3, which would be positive 6. So I kind of took out the step of having the second fraction here and the minus and then distributing. I just did it all together and just put it over one fraction. All right. I just had to make sure I distribute that negative goes with the 2. So negative 2 times this gives me negative 2x, and then negative 2 times negative 3. This is the biggest mistake I see, guys. People forget when they're subtracting to distribute that negative to the second distributive term. Negative 2 times negative 3 is positive 6. All right, now let's go ahead and simplify. 5x's minus 2x's are 3x's. 15 plus 6 will be plus 21. And then my denominator will be x minus 3 times x plus 3. Now let's see if I can do any simplifying here. I'm running out of space. Let's see if I can do any more simple. This would be the numerator. I could pull out a 3, and it would leave me with x. And then 3 divides into 21 and leaves me with 7. So if I multiply that back out, I get this. So I have 3 times x plus 7 on the top, and then I would have x minus 3 times x plus 3 on the bottom. I was hoping this would leave me with an x plus 3 and I can cancel, but it doesn't. So this is your final answer, or you could leave it like this. And that would be the expression that would represent the other piece of the board. Okay, number 12 says, is the relationship between the variables in the table a direct, an inverse, or neither? If it's direct or inverse, write a function to model it. Real quick, direct variation, y equals k times x. This would be slope-intercept form. That would be the slope. And your y-intercept, of course, would be 0. So direct variation is just a line that goes through the origin, okay? It could, as one increases, the other increases, or as one increases, the other decreases. These are both direct variation. As x increases, y could decrease. As x decreases, y could increase. So it could have a negative constant or a positive constant. Now with inverse variation, y varies inversely as x by some constant. So that means as my x values get bigger, there's some constant here, but as my x values get bigger, this fraction, the denominator would get bigger and this whole thing would get smaller. So as x gets bigger, y would get smaller. That's what my inverse variation would be. And as x gets smaller, y would get bigger. Okay, so you're looking at something like this. As x gets bigger, y would get smaller. And as x gets smaller, y would get bigger, up to a point where x can't be 0, of course. So I'm looking at these two. And how do I tell what I have? Well, this one looks like it's actually increasing, okay? Because from -4 or -7 and -4, these are increasing. And this looks like it's decreasing. So one might think, well, inverse variation, but remember, I can have a negative constant here. So I really need to figure out which one of these works. So my constant for direct, okay, so this is my direct variation. My constant, to figure out that, I would divide both sides by x, and my constant would actually be y over x. And remember, slope is the change in y over the change in x. Okay, so that would be my constant. If y divided by x, if all the y's divided by the x is constant, I have a direct. Inverse variation, my constant, if I multiply both sides by x, my constant would be x times y. Okay, that would be my constant. So if it's an inverse, I would multiply these and get a constant. Well, it looks to me like it could be an inverse, so let's go ahead and try. What's 105 times -7? I'm going to get -735. So this is x times y. X times y, if I go 60 times 4, I'm going to get -240. Okay, these are not the same. So I do not have an inverse variation. I do not have a constant, a same for each y. This is x times y. I get 735 here, I get 240 here. So it's not inverse variation. Let's go ahead and try direct variation and see if it's maybe a negative direct variation. I'm going to go y over x. So let's go y divided by x. I'm going to go 105 divided by 7. So this is going to be my y's over my x's. 105 divided by -7, sorry, it's going to give me -15. Well, 60 divided by -4 is -15. 45 divided by, those aren't negative. 45 divided by -3 is -15. And -30 divided by 2 is -15. I have a constant. It is y over x. I have a direct variation. So I'm going to go ahead and say it's direct. It's not inverse. Let's go ahead and circle that. It is direct. It is not inverse. And I'm going to go ahead and write a function to model it. So I'm going to say the y is equal to my constant, which is -15 times x. Is y -15 times x? Yep, -7 times -15 is 105. -4 times -15 is 60. -3 times -15 is 45. And 2 times -15 is -30. There's my equation, and it is direct. So check your constants. Y over x, that constant would give you a direct. And x times y, that constant would give you an inverse. Suppose that x and y vary inversely. X is 5 when y is 8. Write the function that models the inverse variation. Okay. So we know the inverse variation model looks like this. Y equals some constant k divided by x. Okay. That's how we vary inversely. X is 5 when y is 8. So I'm going to plug that in. 8 for y equals your constant, and 5 for x. Now to solve for k, I just multiply both sides by 5. And we already knew back there, to get our constant for inverse variation, you go x times y. So you don't even have to do this. But 8 times 5 is 40. 40 equals my constant. Okay. Now we're going to write a function that models this inverse variation. And it looks like this. Y equals my constant, which is 40, over x. So there's my constant, and there is my model. Okay, soccer team. All right, a soccer team's collecting money to buy their coach a present. This table represents the cost per person for the gift compared to the number of people contributing. So obviously, if more people contribute to the present, you get to pay less, right? What function models the data? How much per person will it cost if all 40 players contribute? Okay, so 40 players on a team's a lot, but all right, let's go ahead and look at this. It looks like as X values are increasing, your Y values are decreasing. Does that happen as a constant rate? Is that an inverse variation? Well, like we did on that last model, X did increase and Y decreased. It doesn't necessarily mean it's an inverse variation. You have to check it. With inverse variations, remember Y equals some constant divided by X. To figure out that constant, you would go multiply both sides. You would go the X value times the Y value equals the constant. Now here, our X value is actually the number of players, and our cost, or the Y value, is the C. So this actually be this would actually be your cost is equal to whatever that constant is, divided by the number of players. So if you want the constant, you would multiply both sides by n, and the constant would be the cost times the number of players would be that constant. Okay, so let's check. Is C times n a constant? That will let us know if we do have an inverse variation. Well, 5 times 40 is 200. 8 times 25 is 200. 15 times 13 is not quite 200. It's 195, but almost, depending on if they rounded that $13. 20 times 10 is 200. It looks pretty constant to me. So I'm going to say the cost times the number of players is 200, right? Whatever that cost is, the cost per player times the number of players is 200. So we're spending $200 on the coach, right, for a gift. So let's go ahead, and what function models this data? We're going to say the function is the cost times the number of players is 200, or if you want to say the cost is 200, the constant, divided by the number of players, or Y equals 200 divided by X. So both of these will work as the function model. How much per person will it cost if all 40 players contribute? So 5, 8, 15, 20, what if all 40 contribute? You just say, well, the cost is 200 divided by all 40 players. And you're just going to go 200, these cancel, so 20 divided by 4 is just 5. So the cost would be $5 per player. So that would be a lot cheaper. Okay, suppose that Y varies directly with X and inversely with Z. So you can have a function that does both. So we're going to write that out. Y varies directly, some value constant times X, and then it varies inversely with Z. Okay. Some constant divided by Z. And then we're given Y is 12. So we're going to go Y is 12 when X is 28 and Z is 7. Here's our constant. Write the equation that models this relationship, then find Y when X is 3 and Z is 3. So we need to find a function that models this relationship. We can do that by figuring out what K is. So we can figure out what K is by solving for K. So I'm going to multiply both sides by 7 over 28 to eliminate this. Multiply this side by 7 over 28. And if I do the math on that, I'm going to go 7 times 12 and divide that by 28. And that's going to give me 3. So my constant of variation here is 3. And it's a direct and an inverse. So it's a jointly. So Y is going to equal 3 times X over Z. There I have my function. Now I'm going to go ahead and figure out Y if X is 3. So I'm going to plug in 3 for X. And I'm going to go Y equals 3 times 3. And Z is 3 over 3. So 3 times 3 is 9. And 9 divided by 3 is 3. So Y is going to equal 3 when that happens. So here I have a function. And here I have the solution when X is 3 and Z is 3. Y is also 3. Okay, if we want to graph this, we have the basic parent function. Remember, when you're dealing with a reciprocal function, just the basic function y equals to 1 over x. Okay, and the inverse function is a reciprocal function. You have a value here. That would be your constant. That would be an inverse function. Just this basic function. Let's look at what that looks like. I'm going to graph it at Desmos real quick. I'm going to pull that up. Okay, I went ahead and typed in y equals to 1 over x. Now you can see here, I have a vertical asymptote at x equals to 0. That happens to be the y-axis because that's where x is always 0. Now look at at your function. If I put a 0 in for x, I'm dividing by 0 and I can't have that. So that is a value my graph cannot touch. It can never touch 0, hence the asymptote. Now, I do also have a horizontal asymptote at y equals to 0, and that's because the degree of my numerator is less than the degree of my denominator. So that's going to be there unless I shift up or down. Now, this is your basic parent function. I have y equals to 2 over x. This 2 is actually going to stretch me and just get taller quicker, okay? If I did 10, it would stretch me and get taller quicker, even more so, okay? So that's your stretch. Now if I take my regular parent function, and just like before, if I do minus h value, let's say minus 3, okay? Let's put that all in parentheses. Let's go x minus 3. That's going to shift me. Remember, inside the parentheses, it shifts me opposite. So I did minus 3, and I shifted my graph to the right 3. Okay. Now on the outside, if I add or subtract anything, if I add 2, it shifts my graph up 2. So it's the straightforward shift up or down. All right. So let's go ahead and look at our regular function. And this also goes for 17. You can see here's my parent function, y equals to 1 over x. Now this, y equals to some a value over x minus h plus k, just like we've done with all of our basic parent functions. The a stretches or shrinks. The h, remember this is the opposite inside the parentheses, that shifts us left or right. The k shifts us up or down. So you can see this will shift us left 3, up 1, and stretch by 2. So it would be the same graph, but shifted to the left 3 and up 1. So let's go ahead and graph both of these. I'm going to pull up a little graph. Okay, what I know about my rational functions, I can't have x be 0, so we're, x is 1 here, negative 1 here. X is 0 right here on the y-axis. So I'm just going to draw my line. That is a horizontal asymptote. I'm sorry, that's a vertical asymptote. It's my where x can't be. Now I know I also have a horizontal asymptote, but we'll talk about that just with our graph. Let's just plot points and see what happens. I like to put 0 in the middle. When I plug in 0, I have an undefined. Okay, I can't have 0. But let's just plug in 1. 2 over 1 just gives me 2. When I plug in 2, 2 over 2 gives me 1. When I plug in, let's try 3. 2 over 3 is 2/3. 4. 2 over 4 is 1/2. And as I get bigger and bigger, this is going to get smaller. It starts at 2, 1, 1. So it's going to get smaller. If I go over 1, I go up 2. Over 2, up 1. Over 3, I go up 2/3. Over 4, up 1/2. And it's just going to get smaller and smaller and smaller. I can see that. Now what happens as I get more close to this 0? Well, I'm going to have to plug in some fractions. What happens when I plug in 1/2? Well, 2 divided by 1/2, I flip the fraction and multiply, it actually gives me out 4. So when I plug in 1/2, I get all the way up to 4. 1, 2, 3, 4. And you can see if I plug in, let's plug in a 4. I'm going to go 2 divided by 1/4, flip the fraction, 2 divided by 1/4. Okay. I'm going to keep change, keep the first, flip the second to 4 over 1, change to multiply. That actually becomes 8. So I plug in 1/4, I get out 8. When I plug in 1/4 right here, I go all the way up here to 8. So this is going to start hugging my vertical asymptote. Now try the negative values. Try some negative values and see what happens. You know you can't be 0, but you can be negative. So go ahead and try -1. 2 over -1 is -2. Try -2. 2 divided by -2 is going to be -1. So it's going to be these same values, but negative. Try -3. 2 over -3 is -2/3. So I'm going to go -1, -2, -2, -1, -3, -2/3, and it's going to start curving up this way. And you can also see, you can imagine it's going to curve down this way. Try some fractions. Try -1/2. Well, same thing happens. 2 divided by -1/2. Keep the first, flip the second to 2 over 1, and it's a negative. change the divide to a multiply. So 2 times 2 is 4 over -1 just gives you -4. So when I plug in -1/2, I get -4. So all these same values, just negative. -1/2 gives me -4. And I'm going to just look like this. So there is your graph. And it just goes a little bit bigger than it would have if this were a 1. It stretches quicker. It gets taller faster. All right. So there's my 16 graph. I stretch it, and I can see just by what I'm getting, I am going to have a horizontal asymptote right here. Okay. Now let's take the same graph. Look, it was the same graph, but I'm going to shift to the left 3, and I'm going to shift up 1. So if I shift this to the left 3, now I can see x cannot be -3. If x were -3, this would become 0. So I'm going to shift my vertical asymptote to the left 3. 1, 2, 3. There is -3. Okay, there's going to be my vertical asymptote because this shifts my whole graph to the left 3. This shifts me up 1. So now instead of having my horizontal asymptote at 0, now it's going to be at 1. So I took this and I shifted it left 3, up 1, and I'm going to have this same graph, okay? So instead of the point over 2, up 1, I'm going to go here, over 2, up 1, and I'm going to land here. And I'm going to have something like this. Okay? And then the same thing, instead of back 2, down 1, from here I'm going to go back 2, down 1. I'm just sketching it. I'm not being accurate here. This is a sketch, but I do know this is my vertical and this is my horizontal because I took my vertical asymptote and I shifted it to the left 3, and I took my horizontal asymptote and I shifted it up 1. I went left 3, up 1. And I just took that same graph and I resketched it. Now on the test, you'll have some choices, some multiple choice choices. So you should be able to see your graph just by shifting your asymptote from your original graph. Now, if you're not sure, take this, always just plot points. Do X, Y points. What happens when I plug in points? Plug in 0, plug in 1, plug in 2, see what values you get out. If I plug in, let's see, plug in 1. If I plug in 1 here for x, I'm going to get 2 over 1 plus 3, which is 2 over 4, which is 1/2. 1/2 plus 1 would be 1 and 1/2. So I'm going to have the point over, here we go, over 1, up 1.5, which is right where I was. And just start plotting points. It's so much better if you know the original and you can shift it though. Plotting points can take forever. All right. Okay, we're going to write an equation for the translation of y equals to -2 over x, and then it has this as these as asymptotes. Okay, x equals to -3 and y equals to -2. Now remember, our parent function is y equals to 1 over x. Okay, this is a translation. When we have an a value here, it stretches or shrinks. If it's negative, it's going to flip over the x-axis. Okay. So we can have an a value over x, and we can have an x minus h, that's our shifting, and then plus k. So this shifts us left or right, this shifts us up or down. So if we shift our x value, and if we look at our graph, if we shift it to the left 3, this is going to be x minus -3. So our h value here would be -3, which actually is x plus 3. Okay. And this is y equals -2. It shifts us down 2. So this k value is going to be -2. Now, if these are asymptotes and that was our value, -2 was our value, our equation is just this, y equals to -2 over. The asymptote was at x equals to 0. That's where a regular asymptote is, x equals to 0. If I shift to the left 3, I'm going to go x plus 3, always the opposite. And if my new horizontal asymptote is always at x equals to 0, excuse me, y equals to 0, sorry about that, which is the x-axis. Okay, y equals to 0. If I move it down to y equals to -2, down 2. Here will be my new horizontal asymptote, and then let's go x equals to -3, -1, -2, -3. Here's my vertical asymptote. This is where I have my asymptotes. I'm shifting down 2. So I'm going to go -2 over x plus 3 minus 2. So this is my left-right shifter. This is my up-down shifter. This is my x shifter. It's the opposite. This is my y shifter, and it's straightforward. So it's going to be x plus 3 minus 2. And it looks like this. So really, you're just plugging in your asymptotes here. So your vertical asymptote goes with the x value. Your horizontal asymptote goes with the y value. All right, what are the points of discontinuity? Are they removable? Basically, all we're doing here is looking for where is my denominator equal to 0? Because my graph can't be that. I can't divide by 0. So what I'm going to do here is factor my denominator. Okay, let's go ahead and factor it. This will be x and x. I need to know the factors of 42 that might add up to being -13. And let's see, 42 is 7 times 6. And 7 plus 6 will give me 13. I want negative. So if I go negative, negative, I get a positive. And negative plus a negative. So let's go -6 minus 7. And I said that opposite, -7 minus 6. It doesn't matter. So this factors into this. So what I can see right away is my denominator. X cannot equal to 7. And x cannot equal to 6. Now here's my question. What are the points of discontinuity? They are x equals to 7 and x equals to 6. Those are my points of discontinuity. Now, are they removable? Meaning, if I simplify this, am I going to end up with an asymptotes here, or are they removable? Are they just a hole in the graph? Well, you can tell that by go ahead and reducing your rational expression here. If you reduce it and they divide out, then they are removable. So x minus 7 does divide with x minus 7 and gives me 1. X minus 6 divides with x minus 6 and gives me 1. So this is really just y equals to 1. This whole thing is y equals to 1. So if I were to graph y equals to 1, I would go, well, where is y1? Here's 1, 2, 3. Y is 1 right here. X could be 1, y would be 1. X could be 2, y would be 1. X could be 3, y is always 1. So basically I would have this line at y equals to 1. I don't even have a rational what you would think the graph would look like. However, x cannot be 7. 1, 2, 3, 4, 5, 6, 7. There's a hole there at x equals to 7. So there's a problem when x is 7. My function's not going to work because my original function wouldn't happen. This wouldn't happen if x were 7 because this would be 0 and then I couldn't even do this simplifying. So 1, 2, 3, 4, 5, 6, at 7 I got a hole. Also x can't be 6. At 6 I have a hole. Okay, so these are removable. They're not asymptotes. They're actually holes in the graph. So here they are. Are they removable? Yes. All right, let's go on to 20. Describe the vertical asymptotes and holes for this graph. So to tell where our vertical asymptotes or holes are, we check our denominator and see where that would be 0. So I would say it would be at when x is equal to -4. This could be a vertical asymptote, or when x is equal to 3. Now I can tell if they're asymptotes or holes depending on if they're removable or not. And you go ahead and reduce to see if they're removable. Well, x plus 4 divides into x plus 4 and leaves you with 1. These don't reduce, so I'm left with x minus 4 over x minus 3. That's equal to y. So what happens is this is removable because what I'm left with my reduced equation is x minus 4 over x minus 3. So x minus 3 stays. This is a vertical asymptote. Okay. X minus 4, or excuse me, x equals to -4 is removable. It turns into a hole. It's simply a hole. It's no longer a vertical asymptote because it went ahead and canceled out. So I have a vertical asymptote at x equals to 3 and a removable discontinuity at x equals to -4. That's my hole. Okay, this one didn't ask me to find the vertical asymptotes, which I could do by looking at my denominator. Where is x not able to go? It asked me for my horizontal asymptotes. So here's our rule. You're going to look at the coefficient of the, or excuse me, you're going to look at the degree of your polynomial. Okay, so if we say the degree here, let's go ahead and say if x to the m over x to the n, we're going to look at the largest degree. If m is greater than n, okay, if that one is bigger, all right, if this is bigger, you have no horizontal asymptote. You're not going to worry about it. You actually have a slant asymptote, okay? You would have to divide them out and figure out an equation for a line. Okay, so we're not going to worry about if that's bigger. If these are equal to each other, so if m equals n, so this one has no horizontal asymptote. But if those two are equal to each other, the degrees are equal to each other, then your asymptote is the reduction of the coefficients. So it's just going to be -3 over 3, which is equal to -1. So my asymptote would be where y is equal to -1. Okay, it would be the coefficients of the term with the highest degree. All right, now if this degree is less than this degree, so like we were looking at with our reciprocal function, this degree would be less than this. This is 1 and this would be 0. Now if that's the case, then your asymptote is just y equals to 0. That's your horizontal asymptote, unless you shift by going up or down by k. Okay, but otherwise your asymptote would just be y equals to 0. So if this is less than this, you have y equals to 0. If they're equal, it's their coefficients. If this one's bigger than this one, you don't even have a horizontal asymptote. So really you're just looking for when they're equal, you have the coefficients, or when this one is less than, so like that's a 2 and that's a 3, then you just have the y equals to 0. All right, so let's go ahead and look at what we have. These are equal, so I'm going to do the coefficients, and I think I already did this. Coefficient would be y equals to -3 over 3, and that's -1. So y equals to -1 would be my horizontal asymptote. All right, what's the graph of this rational function? So here's what we want to do. Find your asymptotes, okay? So your vertical asymptotes will be where this is 0. And you're going to go, well, where 2x minus 4 equals to 0, what makes the denominator 0? Add 4 to both sides, you get 2x equals to 4. Divide by 2. X is equal to 4 over 2, or 2. So if this was 2, 2 times 2 is 4, and 4 minus 4 would be 0. So I'm going to have vertical at x equals to 2. So there's one asymptote. Now let's look at our horizontal asymptotes. Now we're going to go ahead and look at the coefficients of the largest, the degree of the largest term here. And you can see our degree is just 1 on top and bottom. They have the same degree. So on my asymptote, it's going to be y equals to the coefficient of these terms, -2 over 2. And that will be -1. So my horizontal is going to be y equals to -1. All right, and there's that. Now let's go ahead and look at some intercepts, okay? When x equals to 0, I have y-intercepts. So let's look at where x is 0. If I plug in 0 here, let's look at where x equals to 0. If I plug in 0 for here and here, I'm going to get 2 times 0, which is 0, plus 3. And if I plug in 0 here, I get 2 times 0, which is 0, minus 4. So if x equals to 0, y will be -3/4. So there's one point, and you can look at it like on an xy graph. If you plug in 0 for x, you get out -3/4 for y. Okay. So let's go ahead and see what I have. I have a vertical asymptote at x equals to 2. So 1, 2. Here's a vertical asymptote. I have a horizontal asymptote at y equals to -1. So here's y equals to 0, y equals to -1. There's my horizontal asymptote. Okay. I know when x is 0, I go over 0, I go down 3/4. So I'm right here. So what does the rest of my graph look like? We'll plot some points. What happens when x is 1? Let's plug in 1. If I plug in 1 here, I'm going to get -2 plus 3 on the top, and I'm going to get 2 minus 4 on bottom. So if I simplify this, I get 1 over -2. When I plug in 1, I get -1/2. So if I plug in 1, I get -1/2. Let's see what I plug in all these points. I can see it's going to start to hug this way and this way, right? I can go ahead and sketch that. Now let's go ahead and see what happens on this side of the graph. So I want to know when x is 1, 2, 3. What happens when x is 3? Where does that land me? Let's see when x is 3. When I plug in 3, I get -2 times 3, which is -6, plus 3, over 2 times 3, which will be 6, minus 4. So on the numerator, I get -3. On the denominator, 6 minus 4 was going to give me 2. So I get -3/2. -3/2 is -1.5. So I'm going to go over 1, 2, 3, and I'm going to go down 1.5, right about there. And you can see as I go this way, it's going to get closer to -1. If I go this way, it's going to get closer to this graph, this line of x equals to 2. Go ahead and sketch that because you have an idea of what it should look like. And there we go. There's our sketch of this graph. And you're going to have a multiple choice, so you should have an idea of where your vertical and horizontal asymptotes are first and what your graph should look like and plot a few points. All right, let's look at 23. Solve the equation, check the solution. You have to check your solutions when you're solving rational equations, especially if you multiply by variables, because oftentimes you create extraneous solutions. Or you might have a solution that would make your denominator 0 and it's not valid. Check your solutions. I don't want you to get these wrong because you didn't check your solutions, all right? So if you come up with an extraneous solution and you pick that as an answer, you're going to get it wrong. Go ahead and let's work this out. In order to get rid of my denominators, I have to multiply by the least common denominator. X squared minus 25 is actually x minus 5 times x plus 5. All right, so this, to get my least common denominator, I have an x minus 5 and an x plus 5 in each of these terms, and it's here in both terms. So this would be my least common denominator. Now, if I multiply both sides of the equation by it, my denominators will fall out. So what I have here is x over x minus 5 times x plus 5 plus 4 over x minus 5 equals 2 over x plus 5. Now I'm going to multiply both sides of my equation by my least common denominator to get rid of my denominators. So I'm going to multiply both sides by x minus 5 times x plus 5. I'm just kind of writing it to the side here. I'm going to multiply by x minus 5 times x plus 5. If I multiply both sides by the same thing, I'm keeping the balance. All right, so multiplying this side, the x plus 5 and the x plus 5 cancel, and I'm left with 2 times x minus 5. So I'm going to distribute that and write 2 times x, and then 2 times -5 will be -10. So that's this side equals. Now this side I have to distribute. I have to do this times this, and then this times this. So when I do this times this, the x minus 5 and the x minus 5 cancel, and x plus 5 and x plus 5 cancel. So this, I'm just left with x, okay? Now I'm going to undo those because now I have to multiply it by this. So here I was just left with x. Now I have to do it times this. The x minus 5 and the x minus 5 cancel, and I'm left with x plus 5. So x plus 5 times 4 would be plus 4x, and then distribute the 4 to the 5, plus 20. So you had to do this times this. These all canceled and just left me with x. Then this times this. just those cancels, and I had to do x plus 5 times 4, 4x plus 20. So no more denominators, yay, and I'm left with simplifying. X plus 4x would be 5x plus 20 equals 2x minus 10. Get all the x's together, subtract 2x to this side, and you're left with 3x, and then subtract the 20 to this side, and you're left with negative 10 minus 20 will be negative 30. That was a 20. It doesn't look like a 20, right? And then go ahead and divide by 3, and I'm going to write it over here. X equals negative 30 divided by 3 is negative 10. There's my solution. I have to check it to make sure it's okay. Okay, so go ahead and plug this in and see if I put a negative 10 here and square it, this denominator is okay. If I plug in a negative 10 here, negative 10 minus 5 is negative 15. And if I plug in negative 10 here, negative 10 plus 5, none of these give me 0 for a denominator, so this is good. This works. All right, number 24, here I have my problem. X squared minus 16, let's factor it into x minus 4 times x plus 4. So I'm going to write this over here. I have 8 over x minus 4, not times, over x minus 4 times x plus 4. And then that's minus 1 over x minus 4, and that equals to 1. Now, in order to get rid of the denominators, I'm going to go ahead and do my thing where I multiply both sides by the least common denominator. They each have an x minus 4 in common. This one's missing an x plus 4, and this one's missing x minus 4 and x plus 4. So this would be my least common denominator. Multiply both sides by x minus 4 times x plus 4. Multiply this side by it, and then multiply this side by x minus 4 times x plus 4. All right, so multiply this. I'm just going to get x minus 4 times x plus 4. Okay, nothing cancels. Multiply this, I have to distribute first to here, then to here. So when I do this, the x minus 4 and the x minus 4 cancel, x plus 4 and x plus 4 cancel, leave me with 1, and I'm just left with 8. Now distribute to here. The x minus 4 and the x minus 4 cancel, and I'm left with x plus 4 times 1, and that is a negative. So I'm going to go minus x minus 4, or excuse me, x plus 4. Okay, this times this would be x plus 4, and that's a negative. It has to distribute to both terms. That's why I left the parentheses. And there's my equal sign. So I'm going to have 8 minus x distribute minus 4. That distributing is what messes most people up. Careful when there's a minus, guys. That has to multiply by that, and then that has to distribute to both terms. Multiply this back out. This is going to be x squared. Distribute, distribute. This is the difference of perfect squares. It's going to be x squared minus 16 when I multiply. Since I have a square, I'm going to have to get everything to one side and maybe factor or see if I can use quadratic or square root. But let's get everything to one side since I have a square here. So let's first simplify. 8 minus 4 is just 4. So 4 minus x equals x squared minus 16. And then I'm going to go ahead and add x to this side. That eliminates that. And then subtract the 4 also to this side. Okay. So now on this side I have 0 equals x squared. And then I'm going to have plus x. And then I'm going to have negative 16 minus 4, which is going to give me minus 20. So this is all on this side, and this side has 0. Now I can go ahead and try and factor this. 0 product property. X goes here and x goes here. The factors of negative 20, that might give me positive 1. What are the factors of negative 20 that would give you a positive 1? 5 and 4 give you 20. You want that negative and that positive, so you're going to go minus 4. This gives you negative 20, and this added gives you positive 1, so it's going to be plus 5 minus 4. That equals to 0. So solving this times this is 0. What makes this 0 if x were negative 5? What makes this 0 if x were 4? So my solutions would be x equals to negative 5 and 4. However, please don't write that as your solutions unless you check them. Check the solution for extraneous solutions. Go back to your original problem. Here it is. If I plug in -5 here, does that make my denominator 0? No. -5 here? No. We're good. Plug in 4. If I plug in 4 here, 4 minus 4 makes this 0. X cannot be 4. That is one of my no-nos. If I plug in 4 here, 4 squared is 16. 16 minus 16 makes this 0. It doesn't work for either of these. You have to cancel that one out. It's extraneous. Your solution is only x equals to -5. If you give me this as a solution, you're going to get it wrong. And careful, you'll have a multiple choice and both of these will be there to throw you off. So it's going to check to see if you're checking your solutions. All right, guys, last one. Get rid of these denominators. Your common denominator here, they both have an n in common. And then 3 and 5 don't have anything in common, so you're going to have to multiply those together. So your least common denominator will be 15n. So I'm going to multiply both sides of the equation by 15n. Okay. Distribute to both terms. So I'm going to go 15n times 1 over 3n, and I'm going to go ahead and go like this. Well, 3 divides into 15 and leaves me with 5. And n divides into n and leaves me with just 1. So this is going to leave me with 5. 5 times 1 is 5, and then this canceled with this and just left me with 5. All right? And if it's easier to see, maybe I'll write it out like this. This will be 15n times 1 over 3n. And then I'm going to do plus 15n times 3 over 5n. So I'm just going to distribute this and this like this so you can see it. And then that equals -5 times 15n. So I'm multiplying both sides by 15n and I'm distributing here. So this divides into this and leaves me with 5. 5 times 1 is 5. This divides into this and leaves me with 3 because 5 goes into 15, leaves me with 3, and divides into n, leaves me with 1. 3 times 3 is 9. And that equals to -5 times 15 is what's 15? 70? No. Yes, -75n. Okay. 5 and 9, that's 14 equals -75n. Then divide both sides by -75. Divide by -75. N is going to equal to 14 over -75. Now you can leave this as a fraction or change it to a decimal, but just check it. Is 14 over 75 going to make that 0? No. Is 14 over -75 going to make that 0? No. So this is a solution and you're good. All right, guys, that is your practice benchmark, chapter 5. Go ahead and work on this. Come to my live tutoring sessions on Thursday if you need any more help, and good luck. Or on Tuesday, Thursday.